So pinches are a good place to start with nuclear fusion because they were the first machine that worked that was not an atomic bomb. And they actually were the first machine to get fusion in a building in 1957 at Los Alamos National Laboratory. But to understand the history, we need to go a little bit further back in time. Early fusion research really derives from the atomic bomb research done by the United States, and it was fueled by international competition between Russia, the United States, and the United Kingdom in terms of who could get there first, who could get nuclear fusion in a building first. And this is all taking place, by the way, at the end of World War II and in the early 1950s. Now, at that time, one of the things that became prominent on the international stage was a claim by Argentina that they had done fusion, which turned out to be complete bogus. So Cold War was in full effect. The United States wanted to foster fusion research. One of the first things the White House did was they put out a solicitation, and they basically had a contest where researchers from around the country could submit ideas for nuclear fusion. One of those researchers was Lyman J. Spitzer, who was an astrophysics and plasma physics professor at Princeton University. His idea was for a stellarator. He came up with it famously while he was skiing in Colorado, and he was going up on the chairlift, and he thought about the ways the plasma could be looped together and ultimately twisted around in a loop, and that's what became the stellarator design. And we can talk about accelerators in another chapter. One of the pinch concepts came from a fellow named James Tuck, who was a British researcher by descent, but had moved to the United States to work on the Manhattan Project. He was at Los Alamos National Laboratory at the time, and his idea was to inject current down the center of a tube, forming a basic Z-pinch. So a Z-pinch is probably the simplest form of a pinch. It's the grandfather of the family, if you want to call it that. Essentially what you do is you take a current, you can think of it like a lightning bolt, and it travels down the center of a tube that's filled with material fusion fuel. That fuel vaporizes and becomes a plasma, and then that pulse of electricity creates a compression magnetic force around the outside that squeezes the material down to a temperature and pressure where nuclear fusion can occur. If you've ever seen the IEEE logo, that is a pinch logo. That picture of an arrow being surrounded by a curved arrow is essentially the pinch approach. So Tuck submitted a proposal, and so did Lyman Spitzer from Princeton, and the award was something on the order of $50,000 at the time to develop prototype machines for fusion reactors or fusion devices. This, by the way, was about the same time that the United States built the first super bomb. It's what Edward Teller called the super bomb. It was the first fusion-fission hybrid bomb. And the United States demonstrated that on November 1st, 1952, at the Moynihan Atoll in the South Pacific. The way the bomb works is you do a fission event, so you split plutonium, and that produces X-rays. And the X-rays exit the chamber going at the speed of light, and they are refracted or reflected back into a second chamber, which contains the fusion fuel, which is deuterium or deuterium-tritium, probably deuterium-tritium in 1952. So the X-rays essentially compress the second chamber down to a temperature and pressure where atomic fusion can occur, and this creates a secondary energy release, which creates a super bomb. And so the United States demonstrated this first in 1952, but the Russians were not far behind. And the Cold War was on, and the race to develop more powerful nuclear weapons was also on. And fusion sort of evolved out of that program, like I said. So the United States funded the program, and the program was started at Los Alamos National Laboratory around a pinch approach. At the time, it was super secret and classified, and the number of people involved were low. Below 10 or 20 people were working on the pinch there. One of Tuck's first ideas was to do something called the perhapsatron, which got around a specific problem. So one of the issues with pinches, one of the early issues, was that material would pile up in front of the pinch. So as the squeeze occurred, as the current moved down the center, some of the unfused plasma would sort of pile up in the front and create something called the snowplow effect. It's one of the problems, one of the many problems that occurs in a pinch approach. So Tuck's idea was to maybe move that pinch around in a circle, creating a behapsatron. And this is kind of the early days, and they didn't know about the tokamaks at that time. So it was sort of an idea that would eventually feed some physics research into the tokamaks once the United States started the program in the 60s. But this was unsuccessful. They ended up simplifying the system a little bit, and they tried improving the behavior by doing a theta pinch. Now, a theta pinch is slightly different. In a theta pinch, current goes around the outside of the cylinder, not down the middle. So in one case, you've got current going down the middle, magnetic field around the outside. That's the Z. In the theta pinch, you've got the opposite, current going around the tube, magnetic field going down the middle. This ultimately was the first successful pinch approach that worked. And it occurred in the winter and fall of 1957. Now, I want to back up a little bit before we get to that and talk about some of the things that led up to that. In 1955, in England, John Lawson published his now famous Lawson criteria paper, laying out what it would take to get nuclear fusion power out of a fusion reactor. So Lawson was actually an electrical engineer by training. He was not a physicist. That's an important distinction that most people forget. And engineers look at the balance of energy inside buildings and power plants. One of the first things you learn in school as an engineer is how to do energy balances. You look at the inputs, you look at the outputs, and you try to calculate what it would take to get net. So Lawson envisioned a fusion power plant like the sun in a building. So when you think about the sun, it's a big ball of plasma that's doing nuclear fusion because it's under high pressure and density and it's at high temperatures. And the sun loses energy through two mechanisms. One, radiation, which is solar radiation, which comes off as UV, IR, visible, infrared, X-rays, etc. And then the other is through mass loss. As particles stream away from the sun, the mass will take energy with it. So you got conduction and radiation losses. Those are your two loss mechanisms. The energy generation term is the fusion power that's made, and you can do a volumetric calculation of the number of particles at the densities and temperatures that they're at, and then multiply that by the fusibility, which is a rough term for the cross-section, which we can get into later about what cross-section is. But anyway, fusion minus conduction minus radiation. Now, in a power plant, there's also a fourth term called efficiency, which is how efficient your power plant is. That's how that term includes a lot of things like the design of the power plant, the quality of the magnets, the amount of space around the reactor, etc. So net power equals efficiency times fusion rate minus conduction minus radiation terms. And that is the Lawson energy balance. And it's an important concept that underlines practically all fusion reactors and approaches that are proposed today. They all have some play in each one of those terms. So if you talk to some, just giving you an example, if you talk to an entrepreneur that proposes that they put fusion plasma in the center with the magnetic fields around the outside to hold it, and there's a lot of space around it, that would reduce the conduction losses, right? Because the plasma would have space between it and the wall so that there'd be less conduction of material outside of the reactor. In another example, you might want to have a lot of really hot ions and a lot of really cold electrons, right? Because the electrons are cold, so they radiate less power, so you're reducing your radiation losses. And yet another concept, if you're trying to reach proton-boron 11 fusion reactions, you've got to go about 15 times hotter than just deuterium or deuterium-tritium reactions. And as you go hotter, you're fighting against more radiation losses. So your radiation losses go up as you get hotter. So these are important concepts. And all this can stem from Lawson's 1955 paper, which he ended up being knighted for. And it eventually evolved into the Lawson criteria, which is a very famous meter stick for fusion reactions or fusion approaches, where you multiply the density, the temperature, and the confinement time together to make a triple product. And Lawson's criteria says that you have to hit a minimum triple product to get net power. Now, I can take issue with a lot of the assumptions and math equations that went into that. I don't think Lawson criteria is such a hard and fast rule as most people claim it is. But I do like to think more about the energy balance, because it's easier to think about power plants, concepts, and evaluate concepts and reactor designs from the energy balance perspective. So anyway, this all comes out in 1955 from England. And it's right around the time that the Theta Pinch is developing at Los Alamos. The Zeta machine is developing in the United Kingdom. And the Russians are starting to think about tokamaks at this time. So in the summer of 1957, the United Kingdom claimed in August that they had gotten nuclear fusion. This was a pretty bold statement from the UK, and it came out in August, and they had detected neutrons from fusion reactions on a pinch machine called Zeta. And within a few months, they realized that they had detected the wrong kind of neutrons. So there are neutrons that can be generated in plasmas that have nothing to do with nuclear fusion. They are thermal neutrons that are generated because of other interactions in the plasma. And this will become a theme as we go forward in time, because a lot of fusion reactor concepts, fusion teams will claim that they got fusion because they detected neutrons, and they turn out to be the wrong kind of neutrons based on the energy spread, based on how distributed the energy is. So this was an early example of this, and this was a really big embarrassment for the British. They had to retract their statements, and that laid the groundwork for what came only a few months later in November, December of 1957, when the Americans actually got nuclear fusion for the first time, thermonuclear fusion for the first time in American history and human history, really. Fusion had been studied, by the way, back in Oxford, back in the 1930s. That was done in a particle accelerator, where one particle hits another particle and fusion occurs. And Sir Mark Oliphant was the person credited with that. But this was different. This was bulk reactions in a bulk plasma. And when it occurred, the team that knew about it was only a small team, maybe a dozen people. Jim Tuck, who had worked in the Manhattan Project, was the group leader. And Marshall Rosenbluth was just out of grad school and was working at that group at that time, and he was the theoretician who actually proposed the theta concept. So Marshall Rosenbluth enters the story here, and he's a very young man at this time, and he will go on to be very prominent in fusion and eventually get the nickname the Pope of plasma physics. But when theta worked, the machine that did it was called Scylla One. I always mispronounce this. It's SCYALLA1, Scylla One, and it happened in November or December of 1957 at the Los Alamos National Laboratory. I think this is an important date in human history, and it really is not recognized in history books as the day that mankind silently slipped into the fusion age. And it was super classified at the time. Only a handful of people knew that they had achieved this, including the people I just mentioned. But that occurred. It was a very important day. And it also ushered in the beginning of Los Alamos's pinch program, which would go on for another at least decade, through the 50s, the 60s, and into the early 70s, developing pinch approaches. They actually built multiple Scalias, Scalia 1, Scalia 2, Scalia 3, Scalia 4, Scalia 5, maybe more, as upgrades to these pinch approaches. So one of the problems that occurred with the first pinches were that they were really unstable. As I mentioned earlier, if you think about the physics here, you've got a current going down the center of a plasma tube in a Z-pinch. In a theta pinch, you got a magnetic field going down the center. So what's happening is a force from the outside is squeezing the outside of this plasma. And the surface of the plasma is not uniform because you've got something called Rayleigh-Taylor instabilities. You've got a light fluid that's being pushing on a dense fluid. The surrounding material is light, the inside is dense and getting denser. And that surface breaks up. It forms ripples that amplify as the squeezing occurs. Now, plasma is a fluid that conducts electricity. It's not just a liquid. So if you were squeezing a water column, like water coming out of a faucet, and you were squeezing the outside, you would see ripples occur. But in plasma, those ripples are amplified by electromagnetic forces that form between the two. So this is actually called the interchange instability. And it's where plasma grows, the ripples grow because of electromagnetic forces between each ripple as the compression occurs. And it's one of multiple instabilities that form in a pinch approach. There's also the kink instability, which occurs as a column of plasma kinks up. There's also a sausage instability and a couple other ones. I'm not an expert on instabilities, but there's a lot of different instabilities that occur. So this was immediately apparent to the Los Alamos team that the compression was non-uniform. And that was screwing up how hot and dense they could get their plasma, and ultimately how the whole machine would perform as a reactor. So they were trying to come up with ways to improve this effect. And one of the easy approaches that I think either Marshall Rosenbluth could be credited for or one of the teammates was something called the screw pinch. A screw pinch is a combination of the theta pinch and the Z-pinch. You do the two together in tandem. So the reason why you would do this is because it would improve your squeezing approach. It would improve how stable, how steady that squeeze would occur, and ultimately how good the machine would perform. So they tried this approach where they put a magnetic field, they put an electric current around the outside of the tube and down the center at the same time. Down the center column and around the outside. So they're doing Z-pinch down the center. They're doing current around the outside as a theta pinch. And by doing the two together in tandem, they had this combination pinch they called the screw pinch. And then, of course, they could play games with how much current you put around the outside versus how much you put in the middle. And you're trying to tune all these things to make this thing work better. And this was one of the 5 versions of Scalia that were built in the succession of approaches. You know, at the time, the United States was generous, I would say, to nuclear fusion research. They provided millions of dollars every year, tens of millions of dollars to do whatever the researchers really wanted. And it says a lot now how much more restrictive budgets are for this approach, because at the time it was really kind of open-ended. If the folks at Los Alamos asked for money, the U.S. Defense Department would provide it because they wanted to stay ahead of the Russians, and they really had plenty of money to spend. So they kind of got to do whatever they wanted. They could do a lot of experimentation, and it was a really kind of golden age for nuclear fusion research. But pinches start to die off after it becomes apparent that they are not going to be able to get the fusion events that they want. And in a couple of years, what's going to happen is the ICF program is going to start at Livermore National Laboratory. And pinches are going to become more of an offshoot of studying weapons. So let's jump ahead in time. It's called MAGLIF, which is being produced at the Sandia Z machine, which I'm going to talk about. And the other is the flowing pinch being developed by Zap Energy. So I want to talk about MAGLIF first. So the Z machine was built at Sandia in the 1980s, and it evolved from the ion beam studies that were being done at Sandia from the 1970s to the mid-1980s. There were a series of machines called the electron beam fusion reactor and the proton beam fusion reactor, and these were all different attempts to try to do ICF using beams of particles, which didn't really work out because beams don't want to move from point A to point B. So when they sort of abandoned that approach, they decided to convert the Z machine. They decided to convert the machine into Z, which is a giant Z-Pinch. It's the world's most powerful Z-Pinch machine. And it's famous because there are photos all over the internet of one of the shots on the Z. The way it works is imagine a big circular tank, maybe the size of, comparable to the size of a football field. And it's filled with oil, essentially oil from transformers that reduce the amount of electrical shocks and currents that can occur inside it. Around the outside are pulse power capacitors, which accumulate a huge amount of amperage. So in some versions, some iterations, because this thing has been built and then rebuilt at least twice, and now they're planning for Z3, a third version of this. They have Marx generators, which are big spinning things that build up electrical charge in an area and then can be released. So current is stored around the outside of this big round tank, and then sent inwards across a switch approach and then down electrical conductors in a big pulse power machine that all kind of coalesce in the center, where megaamps are dumped down the center of a target. And Z-Pinch has been used to study a variety of different target approaches and different configurations. Some of that work is classified because it's related to weapons research. But so in one iteration, just one version, just as an example, current is dumped down lead wires that sort of sit around in a cylinder around the outside. And what happens when the current goes down is that the wires vaporize, and they create shock waves which compress the plasma in the center, doing essentially Z-Pinch physics. If you think about it, they're generating those shock waves differently because they're not sending a current, just one bolt of lightning down the middle. They're sending 190 or 180 or 90 bolts of lightning around the outside that are creating these shock waves that are penetrating the center target. But it's doing the same thing. Essentially, it's creating a compression wave around the outside that's squeezing the cylinder and squeezing material down to temperatures and pressures where fusion can occur. Now, one of the things about Z that makes it special is that because you do it this way, you really aren't limited, and you can get really, really hot plasmas. 10 times hotter than an ICF approach, or far hotter than a tokamak. So it's not good for studying fusion so much as it's good for studying the extreme conditions of matter and plasma, like in supernovas and stuff. So this approach is kind of it doesn't really work as well for a fusion reactor concept, but it is a great way to study extreme conditions of matter, and also it can be applied to weapons research because the United States can now just do in a room in a building, can do extreme conditions, really high temperatures, really high densities, much higher than a tokamak, much denser than an ICF implosion. And that's what Z machine is good at. So if you look at the schedule for Z machine, a certain percentage of its uses is for fusion research, but some of it's for weapons, and some of it's for astrophysics tests, and some of it's for finding out the equation of state for lead at 100 billion degrees temperature or something like that. So it really has a multiple use facility. It's a multiple use facility, and part of it is classified. But it is an extreme tool in the United States scientific arsenal, and I'm sure that the United States should fund the Z machine upgrade to get even further on in extreme conditions. But in terms of fusion, one of the things that it does is an approach called MAGLIF. MAGLIF is where plasma in a column is compressed like a pinch, and as I mentioned earlier, material can pile up in front of the pitch and be pushed out the top. So it kind of creates a snowplow effect where material is pushed out the top that's unfused. So one of the things you can do is you can zap it with a laser beam, either down the center as a preheat or as a post shot to compress and hold in the material. And that is essentially what MAGLIF is. It is a Z-pinch with a laser beam down the middle. And that's what MAGLIF is, and it's been a popular fusion research topic for at least a decade now at Sandia National Laboratory. But it's hard to see how that will become useful for a power plant. I mean, it's a great way to test different things. If you're a commercial fusion company and you want to test your materials at extreme conditions, or if you're the federal government and you want to understand weapons, MAGLIF is a great facility to use. But how do you make that into a power plant? I don't know. It's much more difficult than some of the other approaches that are out there. One of the things I will say about MAGLIF, it pioneered the use of pulsed power. In fact, the entire field of pulsed power evolved out of fusion research because the problem arose: how do you get so much electrical energy into these machines very quickly? And so there's a whole textbook. It's a great textbook that you should check out, Pulse Power Research, that's authored by a whole bunch of folks that worked on various fusion research projects around the country and internationally. And they develop things like energy storage. How do you store a ton of electrical energy in one place? How do you do switches? Because it's not so easy to just flip a switch and dump mega amps of current onto an electrical system. That's a difficult thing. And then how do you make the whole thing modular and safe? These are two huge problems, and pulse power research, the field of pulse power research, evolved to address all these questions for various machines like Jet and Z machine. Well, let's talk about flowing pinches. Flowing pinches are a wonderful innovation that occurred much, much later in the history of pinch machines. We got to zoom into the mid-90s, in 1997, and the story starts with a fellow named Shumlak, who at the time was a postdoc at Air Force Research Laboratory in New Mexico and Arizona area, so out in the Southwest. An Air Force Research Laboratory has a machine called STAR. STAR is very similar to Z, and it dumps current down in the center into the center, and it's a classified machine, but it is used to study nuclear weapons research. Shumlak was working on the STAR machine and studying pinches after he had completed his PhD. He was observing papers that were coming out of the tokamak community where they were seeing something called shear flow stabilization. Essentially, in tokamaks, there was a great deal of shear being, if you think about shear in fluids, for example, you have fluid flow at different velocities from the outside to the inside of the tokamak. And because of shear, it was kind of messing up compression, and it was also stabilizing the flow inside a tokamak. Eventually, this would become like a twisted shear that was stabilized in spherical tokamaks later on in the field. But shear would stabilize flow. And Uri's idea, which was kind of genius, was to apply shear flow to pinches, so that you could get a more stable pinch by applying the shear flow that was coming out of tokamaks. And like everything else, it was an optimization problem. There was an operating window in which it would work, and then a whole bunch of other areas where it would not work. And Uri wrote this out as a theory, where his first papers were providing a mathematical framework for this. So applying the different physics equations to state for plasma physics, and then modeling the shear flow, and then showing that it would be stable. So he comes up with the idea, he develops it a bit, he writes a couple papers, he accepts an assistant professorship position at the University of Washington, so he moves there in the late 90s, and then sort of gets his first seed funding grants about that time to build the first example machine where he would test stabilized shear flow in a pinch. So they started developing the idea in the 2000s. They would inject a current down a cathode that would jump across a gap of about 3 to 4 feet, and they would get compression on the outside, and the flow through the center would stabilize the pinch and allow sort of a continuously flowing material to flow through a pinch structure. And about that time, he employed a series of postdocs and graduate students to also do models of this. So they developed a website, they developed computer graphic models that showed the stabilization to kind of explain the idea better, and did a series of experiments to build up the research. So please forgive me if I'm not an expert in the exact details. I recommend that folks check out Uri Shumlak's website at the University of Washington. But flowing pinches were a very exciting idea because they don't require magnets. They're very small, and they have stable control. At this time, he wasn't demonstrating fusion at all. In fact, I think the first time he's demonstrating fusion is in 2001, 2021, this year, with his publication papers coming out. But this was an exciting idea, and they wanted to get funding from the Department of Energy. Now, at the time, this is like circa 2000 to 2017, or 2010 to 2017, excuse me. At that time, the Department of Energy was culling the fusion research space to prepare for ITER. They were essentially eliminating a lot of sideline projects and trying to narrow the focus inside the U.S. fusion community to support the ITER project. So, for instance, the levitating dipole experiment at MIT and Columbia was canceled, received a serious reduction in funding because the DOE wanted to fund ITER. They also caught the Alcator funding, Alcator CMOD at MIT about the same time. And MIT raised a big fuss about this. They had graduate students go in front of Congress. They did internet outreach. They did AMAs on Reddit. They did a lot of public advocacy to try to keep their funding. They ended up getting an extension from Congress, but the funding was ultimately cut by 2013. So, if you're Uri Shumlak and you're trying to generate interest and funding around a new, exciting fusion approach that's based off of a long lineage of research and some innovations that had come out of the tokamak community, what do? You can't really get funding from Department of Energy. And it was sort of at this time that ARPA-E stepped in and started funding seed projects at the same time. So Uri decided to go private, and I think that was the right decision. But going private is challenging, of course, because nobody knows what a private fusion company looks like at that time. There are only a few examples of private fusions in the world: Tokamak Energy, General Fusion, and TAE. This was before Commonwealth was around. So his first machine was called, his first company, was called Fuse, F-U-Z-E, and they received some ARPA-E seed grants to develop a private company. And sort of it was a weird hybrid between his laboratory at the University of Washington and the private firm. Team was, under 20, 25 people under that at the beginning. And they built prototype machines, and they improved their diagnostics. A lot of these fusion teams, when they start out, that's one of the first things they have to do is you got the concept, but you don't have the data. You don't have the data because you don't have the diagnostics. So it sort of goes in this iterative fashion where you have the concept, you improve the concept by building better diagnostics, which give you more data, which allows you to improve the concept, which then needs you to get better diagnostics, which means you get better data, which allows you to improve the concept, which eventually allows you to build bigger machines and bigger machines because you need more power to get to higher operating conditions and better regimes and get more performance out of your same machine. So I see that sort of path in this sort of cycle around different machines approach that a lot of fusion companies take. In any case, they had the seed funding, they had the seed team, they hired Brian Nelson, who is a professor, to be sort of their liaison between the investment community. And Uri was exceedingly careful about making any kind of claims about his machine. I think he is known in the community as having that reputation. He's exceedingly careful. And he's very precise about his publications. So a lot of respect from the scientific community around his work. Eventually, they did win this funding from Chevron Energy Ventures. They presented at the Rice Energy Technology Ventures Conference in Houston, Texas. Rice throws this 2-day conference that's really in the underground world of venture capital, energy, and fusion, known as a good event for interfacing with large energy firms because, of course, Houston is sort of centrally located. So the ZAP team went there, presented. They reincorporated as ZAP. They got their seed funding from Chevron Ventures, and now they are hiring. And they've actually hired a lot of very good people from other fusion companies and other fusion entities. So they hired a number of heavy hitters that I like, Matt Thompson, and other folks. Anyway, I really appreciate your time. Thank you so much for listening to this little lecture on pinches. We hope to do one on every family of approach. And again, this is grouped around the book, Insider's View of Commercial Nuclear Fusion, which I highly recommend you get. All right, take care.